friends. Yeah, someone should probably tell the world that I'm leading, because it's not clear to everybody. Okay, so I'm Erin Talvitie. I'm a professor at Harvey Mudd College, which, by the way, I always just like to throw this out there because, not because I'm an evangelist, but just because it's part of the world. So Harvey Mudd College is a small, undergraduate-only liberal arts college. There are 800 students total in the school. I teach courses of like 30 students apiece. I have a pretty teaching-heavy job, lots of one-on-one interactions with students, and I do cool research as well, but without grad students. So it's a whole different world than the one that you're immersed in when you're at U of A. Having said that, I want to talk to you about, this is going to be a paper at the Reinforcement Learning Conference, the first Reinforcement Learning Conference. You can see there's a whole bunch of co-authors. Those are all undergraduate students who've worked with me. This project, you won't believe it when I show you what it is, but it has been 5 years of dead alleys and wrong questions and mixing things up and jumping ahead and having to pull back and all of that stuff. And so all of these undergraduates, their work doesn't necessarily directly show up in this talk or the paper, but they did really important work generating negative results and sort of clarifying the ideas and pushing things forward. So, just hold them in your heart. Right, because it's like I don't have a grad student to do all that, so I have to have 7 undergrads. Okay, it's called bounding box inference for error-aware model-based reinforcement learning. I'm not going to explain that right now. Let's talk. Come on now. Okay, I'm going to just draw you my quick picture of model-based reinforcement learning so you have some idea of what I'm talking about. We've got some environment and an agent who is interacting with the environment, and the agent gets to impact the environment somehow, and the agent receives observations of the environment. They sort of see what's going on, and also some reward signal. This is sort of central to the reinforcement learning project, right? So it's like there's some signal that's like, hey, you're doing a good job, or you're not, right? And then, and so what makes it model-based is that somehow, via some process, which I'll call model learning, the agent kind of in its mind constructs a simpler, smaller, more orange version of the environment called the model. Okay, and so you think of it as just like, a model car and a real car, right? It's like a car, but it's different, it's smaller, it's easier to deal with. And so then somehow with the model, the agent will get predictions about the future, and then it somehow uses those predictions in a process that I'm just going to vaguely call planning to then influence its actions, hopefully in a positive way, right? And sort of help it make better decisions in the environment. That would be cool. It doesn't work. So I'm going to show you some examples of it not working in a second. But first, let me talk to you about this example that I'm going to use a fair bit in the talk. So it's called Go Right. We have this agent represented by the purple robot that's all the way on the left. And like the high-level thing here is the agent needs to go all the way to the right for a chance to get a prize, but it receives -1 reward every time it goes right. Okay, so it's kind of painful to go to the right, but then once it gets there, it might be very happy, right? Okay, so I'm going to show you a little bit of what's going on in this environment. So the agent moves right, it gets -1 reward. It goes left, 0 reward, -1. It's, oh, that hurts. Ouch. I'm sad. Oh, that felt better. Nope, sad again. And so on, right? And then, so here we are. The agent's about to enter the rightmost position. And so you've noticed perhaps this light bulb down at the bottom is kind of blinking, right? So it's taking on different values. There are 3 different values that it can take on. And whether or not the agent gets the prize depends on the value of that light bulb. So as it enters the prize location, in this case, the light bulb is not white. It's not at full intensity. And so the agent has not won the prize. And you can tell because the prize indicators have not turned on, right? And then, so what it means that it hasn't won the prize is that if it goes right from here, it still gets -1. And the prize indicators are kind of flashing. They're like, hey, you didn't win the prize. Stop it, right? But if the agent leaves and then goes back in, oh, I guess I flipped the values. All right, so black is full intensity. Sorry about that. So if it enters and the light bulb is at full intensity, then it has won the prize, and the prize indicators say, hooray, you've won the prize. And what it means to have won the prize is every time it goes right, from now on it gets +3, hooray. And so now it's in paradise, right? It just sits there forever, going right. All right, so you can see there's like little complications in this thing. Why are they there? I don't know. We'll talk about it a little bit. The main thing I want to emphasize is, though it maybe wasn't obvious to you sitting there, the status indicator light bulb is fully deterministic. It's just second order Markov. Okay, so what I mean by that is you need to know the last value of the light bulb in order to predict the next value of the light bulb. The last and the current value to predict the next value. Okay, so there's a deterministic pattern of that light bulb. The prize indicators are fully deterministic. Everything about this environment is deterministic. It's just not quite Markov. Okay? So let's go ahead and do Q-learning in this environment. The value function is really just a table lookup over those, the different places, the different things in the environment. But it doesn't take into account the previous value of the light bulb, right? So it's not quite good enough. But that's okay, because Q-learning still does all right. So even though the environment is non-Markov, Q-learning does learn a pretty good policy. What you're looking at here is average discounted return. So it's, if you don't know what that means, that's okay, but higher is better. So the policy that it learns is roughly like, go right, endure all that pain, and then if you get the prize, great. If you don't, go left and go right, and then try to get the prize again, right, until you get the prize. And that's pretty reasonable. It's a good one. Okay, but I'm here to talk about model-based reinforcement learning, which means we're going to have a model, and we're going to use it for planning somehow or other. So let me talk about how I want to use a model for planning in this particular setting. So I'm going to use an idea called model-based value expansion, which I think is a fancy name for an idea, very old idea. But we're going to, here's the idea. So we're going to, if you are in a state in the environment and you take an action, and you end up in a new state and you get some reward. Okay, so that's what we were talking about. You're like, I'm observing things, I'm taking actions, I'm getting rewards, it's great. And then what we often do in reinforcement learning is we calculate a TD target, a temporal difference target, which is going to be an estimate of the value of taking that action in the state where I started from. And that estimate is, oh, I got some reward, and then there's some value of being in that next state. Okay, so that's a one-step target, but I could also extend this experience by asking the model what would happen next. And then from that, I could calculate a two-step target where I've got like, oh, I got some reward in step 1, I got some reward in step 2, and then there was some value of being in that third state. And I could do it, I could extend it even further, right? I could extend it out to 3 steps. And so now I have a 3-step target, which is, some reward, and then some more reward, and then some more reward, and then that state, finally, I landed there, and this is what it's like, how good it is to be in that state. Okay, and I apologize for the math. Some of these slides I wrote at 3 a.m. last night, and so I hope by August in RLC I'll be able to get rid of the math. But here we are. And then the update, for those who are interested, looks like this. So we just take those multi-step targets, and we average them together, and that's our estimate of the value of taking that action in that state, and then we sort of move our current estimate in that direction. That's the idea. If you're not an RL nerd and this doesn't immediately make sense to you, that's fine. You're fine. Okay, so I'm going to do that with a perfect model that makes all the predictions exactly correctly, including the fact that it's second order Markov. So it accurately predicts the light bulb values, even though the value function can't quite cope with that. And here's what happens. So that's great. Looks great, right? So there are a couple of things happening here. It's jumping up very quickly, and that is partly because, what happens is the agent learns, I don't want to go right, because it's -1 every time it goes right. And then it's only once it sees there's a prize at the end that it then has to propagate that knowledge all the way back down the hallway to the very first location that it will finally say, yes, I should go right here. And we start to see some positive things. Yeah.
So does the number of time steps that you're looking at future matter for this learning curve? What n are you using?
Good. It does matter. This is 5. This is a horizon of 5-step updates. Okay, so far so good. The other reason that we're doing better, and especially seems like it's doing better in the long term, that's I think because the perfect model is accounting for that second order Markov dynamics, and I suspect probably the value function is tracking that somehow, and it's probably some interesting stuff. Anyway, let's keep going. But now I want to do it with a learned model, because that's where we want to live. But not really. I don't want to learn models yet. I'm going to pretend I'm learning a model by taking the model that gives the exact least squares estimate of the expected next state. So it's an expectation model. It's predicting the expected next state, except I've done a great job. But the model is not perfect because it can't fully predict that light bulb. Yeah? Okay, so here's what happens. It's very bad. And here's the main reason that it's very bad is that the expectation model for that light bulb, for the prize indicators, because it can't quite predict the light bulb, it sort of thinks there's a probability over those prize indicators, right? It thinks there's a 1/3 chance that they'll turn on and a 2/3 chance that they will not turn on. And so it predicts a value of 1/3 for those lights, which is not a thing in the world. And so we get this behavior. And then some people, when I show them models failing, some people in this room say well, that's because you're going out 5 steps. You won't have a problem if you only go out 1 step, right? No, that's not true. So now I'm going to do Horizon 2 planning, which looks like this, right? So it's like you're averaging together the real Q-learning update and an update that involves 1 step of the model. So there's no multi-steps through the model, and that is also garbage. Yes? Yeah? Oh, this is a great question. Sorry about that. So yeah, what the agent is receiving in terms of observations is a continuous valued variable about its location, a continuous valued variable, a numerical value of the intensities of the lights.
So it doesn't know about its location, but it does. Sorry, okay, so there is a continuous value for the location.
Yep.
And for the lights.
Yep.
And so when you say least square, it was doing the least square prediction, so it's with a continuous value.
That's right. So it's got the values of the values that it perceives in the real world of the prize indicators are 0 and 1. But then because it thinks there's a probability distribution over that, which there isn't, then it gets an intermediate value. Yes, thank you for asking that. Okay, and then another thing you might think if you've done kind of reading in this area is, well, but we know that expectation models are kind of questionable in certain situations, especially when there are probabilities involved. And even there are not probabilities involved, it sort of feels like there are. So it makes sense that expectation models would fail. We should use a sampling model instead. So instead, I'm going to now have a model that is the exact maximum likelihood estimate of the distribution over next states. And then to do my updates, I'm going to sample from that distribution. And that fails too. So I should say, it's exact with a caveat. I made a very common modeling decision, which is I modeled the state variables as conditionally independent of one another given the current state. So that is very common. And why does that cause everything to fail? Well, because at this point, the model erroneously thinks there's a 1/3 chance of each of those prize indicators turning on. So the joint probability of them turning on is now 1/9, which is too small. And so it is underestimating the chances of getting the prize. And so now the agent doesn't think it's worth getting the prize. You see so far? You with me? All right. So, okay. So these are not even learned models, but they're models we could maybe learn. Why are they bad? Like, what causes models to be wrong? One thing that causes models to be wrong, people call it aleatoric uncertainty. It's a very trendy term, but it's a very silly term. I think people should call it outcome uncertainty. Because what aleatoric uncertainty is it's just that, like, even in the real world, there's some inherently random process that means different things might happen even if you're in the same situation. Okay, so it's like, you know, whether or not you believe that could really happen in the universe is a philosophical question. But we can profitably say that, like, a coin flip is an example of this, where it's like, oh, I flip a coin and one thing could happen or the other thing could happen, and roughly speaking, that's a random outcome, right? Okay, so why does this cause models to be wrong? Well, in the sense that, you know, given the same initial starting location, you know, the model, even a really good model, might predict that next state, but what might really happen is that next state, right? So it's not that the model's wrong, it's that it says different things potentially than the world says. And so what you can really only hope for is a model that gives you the same distribution as the world, right? So you would want, ideally, maybe a model that assigns the same probabilities to those outcomes that the world does. Okay, so that's one thing, but that's not the problem, because there's no randomness in this example. So it's not outcome uncertainty. Okay, another possibility is epistemic uncertainty, similarly trendy, similarly confusing. I think you should just call it parameter uncertainty, because what it means is, listen, I collected some data. It was some data, but it maybe wasn't all the data, right? And so from that data, and I train my model, I get a model, right? But if I had sampled a different data set of the same size, I might get a different model out, right? That's the idea, is that maybe we haven't seen enough training to really nail down what model we are actually estimating. And so if you give the same kind of input to both of these models, like here's a state and here's an action, and then you say, oh, you predict, and it might say that, but you say, hey, you bottom model, you predict, and it might say a different thing, because they were trained on different data, and it wasn't like a lot of data. Now, epistemic uncertainty, generally speaking, goes down the more you train. So if you have a data set with lots of data, then usually if your learning process is kind of doing what you usually expect it to do, then it will probably converge down to, like, the best model it can learn. Yeah? And then even if you see a different data set of similar size, it would probably get you to the same place, right? So, like, eventually you kind of get to zero-ish epistemic uncertainty. You're like, listen, I'm doing the best I can. Yeah? Okay, but that's not the problem either, because I fast-forwarded that whole thing. I got us to the exact maximum likelihood estimate, the exact least squares estimate. That's not it either. So what is it? And I'm pausing here because you read papers in this area, and there are two kinds of uncertainty. There's aleatoric uncertainty, and there's epistemic uncertainty. And I want to deal with one or the other or both. But they're wrong. There's another one that's really important. Another reason your model might be wrong is because it's just bad at its job. So I'm going to call it model inadequacy. In different settings, you might hear it differently. You might call it underfitting. You might call it misspecification. But the idea is there's some limitations in the model learning algorithm, the model representation, that are keeping it from learning a perfectly accurate model. So that even if I get a huge data set, and I have no epistemic uncertainty, so that they all point to the same model, that model is still wonky, right? So I talked about the independence assumption earlier. Like, that's an example of a limitation that might cause this. You might have a neural net with too few hidden nodes, and that might be a reason for this. You might, like statisticians would know that, like, oh, I should be doing a quadratic regression, I'm doing a linear regression, that kind of thing. Okay, that's what this is. Where I've made some modeling decisions, and it doesn't actually contain the real world, which is inevitable. The real world is huge. How in the world is my model going to represent the real world? So, all right. So the problem is that when you've done this, even if it's deterministic, even if there's zero epistemic uncertainty, you're going to possibly see the model predict things differently than the world would predict. Yeah? Okay. I think this is what's going on. I think this is the problem. So today, I would like to talk to you about detecting errors that are due to model inadequacy and then doing something about it. So what does it mean to detect errors due to model inadequacy? Well, pretend we have this generating process that's going to give us data and this like function, and it looks very quadratic, right? And so we get some data from it. If we get a little small data set and we fit a line, right, we fit a linear model, then we're going to get something like this, right? And it's right about some stuff, and it's not right about other stuff. And then just to illustrate, just to remind you what epistemic uncertainty is, like if I had picked a different small data set, then I'd get a very different line, right? But that's not what we're talking about here. We're talking about the world where there's lots of data, and I'm not worried about, I'm not unsure about what the best fitting line is. I know what the best fitting line is. It's something like that one, right? But it's still not a good model. So how do you know when to trust it and when not to trust it? The big idea is if you were a statistician and you fit that thing, you could also ask questions about the noise detected by the model, right? How varied does the model think the outcome is going to be? And if you ask at different points, the model will give you different answers, right? So if you ask here, you'll get quite a wide, it'll be like, oh, it's very noisy out here, right? It's not noisy, it's deterministic. But it doesn't know. All it's got is model error. All it's got is, I was wrong, so it must be noise, right? If you ask it out here, probably be a little skinnier, right? Because it's a little bit closer to right. And then if you ask it in certain places, it'll be like, oh yes, haha, there's no noise here. I know exactly what I'm doing. Yeah? So, and I want to point out that the model is going to make these probabilistic predictions even though there are no probabilities, right? Even though there's no noise, there's no stochasticity, it's still going to make these probabilistic predictions. So what I'm here to tell you is that model inadequacy looks like aleatoric uncertainty. And therefore, we can use methods for detecting aleatoric uncertainty to detect model inadequacy. Yeah? Great. Cool. Well then, how are we going to, if we could do it, how are we going to use it? Well, we're going to do this model-based value expansion thing, but we're going to tweak it just a little bit. For each of these targets, I'm going to give an uncertainty value. And how do I get that uncertainty value? Just hold your horses. We'll get there. So somehow I'm going to measure an uncertainty over each of these possible targets. And I'm going to fix the uncertainty of the first one to 0 because that's real data. I'm not worried about any model errors there. So there's 0 uncertainty about that, but then for anything the model was involved in, I'm going to try to compute some kind of uncertainty. Yeah? And then I'm going to compute a weight. This is a softmax distribution. It's OK. You don't need to know. But if you're interested, that's what it is. And then my update is instead going to take this weighted average over those targets. So now, potentially, if my uncertainties are very high somewhere, then that target will be down-weighted quite a lot and won't have very much influence over my update. Yes?
So yeah, maybe I'll ask like the main question after the talk, but I just wanted to ask, like, are you thinking of like tabular type models or also like functional approximation?
Function approximation is OK. Yeah. Yes. So again, if you're not an RL nerd and you don't look at this and go, ah, OK, that's fine. You're fine. All right? So here's what I'm saying. Let's now talk about the question. What measure of uncertainty should we use? Right? What should these U values be to make this work, like to make this a good idea? All right, well, there's one idea from a paper that I worked on and Martha worked on and a couple of now former students of U of A worked on, Zahir Abbas and Sam Sakota. And the idea is this. It's like, oh, I'm going to switch how I'm representing states. I hope it's OK. Again, last minute slides. So I'm going to kind of show my states in like a phase space. So imagine that the state is 2-dimensional, and this box is that 2-dimensional space. Okay? And so my state is like a point in that space. All right? So imagine that you have a state, a point in the space, and then, you know, as before, we take an action, and then the environment shows us what happens next, and we get some reward, right? So now we want to extend this using the model to make a prediction. So the model is going to, you're going to choose an action, and then the model is going to make a prediction about what will happen. So it will give an expectation value, say like, oh, this is the expected state vector that I expect to see. And it will also give a variance. Okay, so it's going to effectively give us a Gaussian distribution over next state, or a Gaussian approximation of the distribution over next state. And then if we keep pushing forward, then that'll happen again, eventually. Oh, that's the, yeah, right. Sorry, everything's a little pokey. I think it's because of all the technology. Oh, and a Gaussian over the reward as well, right? So Gaussian distribution over the reward, possibly. And then, so you take that same mean, that same mean value, right, that expected state, and you predict the expected next state, and you put a variance over that, right? And so then what is our uncertainty going to be? Our uncertainty is going to be, well, 0 for the first step, right, because we know that was OK, it's real data. But then everything after that, we're just going to add together all of these variances. We're just going to be like, oh, if the variances were big, then probably this was bad, right? Probably we shouldn't trust this. Okay, and in that paper, we roughly found that it helped, right? Like that turned out to be an OK idea. However, if you're quick on your feet, you might detect some conceptual flaws with this plan. For one thing, these are variances over like states, right? So we're asking how uncertain are we about the next state? But that's not the same as how uncertain are you about the value of being in that state, right? Tiny, tiny variation in the state could still correspond to large variation in the value. And huge variation in the state might have nothing to do with the value, right? So it's maybe not a great proxy, conceptually speaking. And then also, what is this adding thing? We're like adding the variances over time? Like what even is that number? It's It's heuristically just like, well, if we had some uncertainty early, then probably we should keep having uncertainty, right? But it's not theoretically motivated in any way. It's not principled. So, you could try it, right? So here, let's try it. Let's do one-step predicted variance, selective MPE, and here's what happens in Go Right. Okay, listen, it does pretty much exactly what Q-learning does, which, listen, I would much rather have that than what the expectation model was doing before, right? But it's still disappointing. What's happening here is that the light bulb is just always uncertain. Always uncertain. But it doesn't matter most of the time. Most of the time, who cares what the value of the light bulb is? And so this thing is way overestimating the uncertainty, and it's not sensitive to where the uncertainty matters. And so it's really just not using the model at all and doing what Q-learning does. Okay, so here we've seen that these one-step predicted variances can be, poor proxies, right? They could be overly conservative, and I also speculate that they could be overly aggressive, but I don't have experimental results for that. Okay, so let's try something different. You're thinking, well, all right, so measuring the variance over the state wasn't the right thing, but and then adding those variances together wasn't the right thing. But I want to reason over time, and I want to reason about the actual update I'm going to make. So I should turn to inference to push my uncertainty through time and through my reward function and through my Q values to get an uncertainty over the actual TD targets. And we can do that. That's not hard at all. We can do that with Monte Carlo inference. So here's how we'll do it. We've got our state. Sorry, I should have fast-forwarded this part. Okay, so here's our initial starting experience, and then we're going to choose an action. And the model is going to predict, again, a Gaussian distribution over next states. But we're going to sample from that distribution some concrete actual states. And so we get some sampled states from that distribution. And then for each of those, we're going to ask the model, hey, what would you say? Oh, and then now we'll get 3 different sampled reward values. And then we're going to ask at each of those states, hey, model, what do you think is going to happen next? And then it will tell us, it'll predict a Gaussian distribution for each of those. And from each of those distributions, we will sample a state. And we'll get 3 reward values, 3 sampled reward values. And those 3 states each have 3 different values, right? Each have a value of their own. So this gives us sampled 3, in this case, 3 sampled TD targets from the model's distribution over the future. So there's 1, which is just the ones from the first sample trajectory. There's number 2, which is just the ones from the second sample trajectory. And there's number 3, which is all the ones from the third sample trajectory. Yeah? And then what will our uncertainty be? It will be like, well, listen, if I'm uncertain about the TD target, then that means I don't know how to update my value function. I'm confused about what direction I should update it in or whatever. And so my uncertainty could be the variance, the sample variance over that population of TD targets. So I know I'm throwing a lot of technical jargon at you, which is not my style, but I hope you're with me. The idea is we're using sampling techniques to get an estimated variance over the updates that we would make. And if that variance is large, then we probably don't want to do the update. Yeah? So, well, let's go back and see how well that does. Ooh. That actually does a lot better. So I'm showing you at 2 different sample sizes, right? So one of them is k equals 10, that's 10 Monte Carlo samples, and k equals 40, that's 40 Monte Carlo samples. More samples, more better. That's pretty common outcome. So far so good. This is looking pretty good. All right, but I want to now burst your bubble a little bit. So the Monte Carlo method here is sampling from a distribution. The distribution came from the model. There is no stochasticity in this environment. The model is not estimating any real probabilistic quantity. Those probabilities don't mean anything. They're coming from frequency of observation, right? Which is going to have to do with how the model is representing things and what its biases are and what its structural assumptions are and the policy that's collecting data, right? All of that is going to influence the frequency at which it observes these things and is going to affect this distribution that the model is making up. So, can we see it? Like, the question is that a problem? And I'm gonna argue yes. So I'm gonna show you now results in a slightly different version of Go Right. I'm just gonna increase the number of prize indicators to 10. There are just 10 lights now, right? Okay, so, oh well, let's just see what happens. Come on back now. And then I'm going to spread out a little bit and show you also results in Go Right 10. Okay, so now the Monte Carlo agent is doing worse than Q-learning. So what's going on? Well, one thing is, with more prize indicator lights, we are multiplying together more 1/3, right? So we have a lower probability, even lower probability of imagining reaching the prize. But that's not the problem, actually, because we should be selectively ignoring that thing. So what really is the problem is that because the probability of that outcome has become so tiny in the model, the variance of the predicted TD targets has also become incredibly tiny, because the likelihood that that one amazing thing will happen has become very tiny in the model, even though the chances of it have not changed at all in the world. Yep. Q-learning is underneath one-step predicted variance. Yeah, it's hiding. It's hiding. So, and you might say, well, that's okay. I will just do more Monte Carlo samples, right? And then I will say, okay, let's do 20 prize indicators, right? So I can arbitrarily reduce the variance of the predicted TD targets to any number, any non-zero number, and it will always indicate the same problem with the model. So even if I had exact inference, right? Like sometimes people are like, you should be using Gaussian processes because then you can have fancier inference. And I'm like, I don't care, because even if I knew the exact probability distribution, it would be worthless to me, because the number itself can be arbitrarily small and still indicate a problem. Whew, that's dark, right? What do we do? Well, here's what I want to do. The problem is that the uncertainty measure we're using is too sensitive to the model's estimated probabilities, and those estimated probabilities don't mean anything. What I want to know is just like, no, seriously, what is the, like, how big and small could it be? Like, how unsure are you? So instead of measuring the variance of these sampled TD targets, I'm going to now measure the range of the sampled TD targets, I think. Here we go. The range, which statistically just means the maximum value minus the minimum value, right? I just want to know, how big do you think it could be, and how small do you think it could be? If the range is very small, and I don't know which one in the range it is, it's probably okay. They're all very similar to each other. If the range is very large, then it really doesn't know what value I should use to update my value function. So let's see how that works out. Come on now. There we go. All right, so this is promising, right? So you can see in the original go right, using the range, the Monte Carlo sampled range is a little bit better with both amounts of samples, which is cool. And then you can see it's definitely doing better in go right 10, right? It seems to be a little more robust, but it's still kind of failing. Why do you think that is? It's because in order to get the range right, you have to sample values at the extreme ends of the distribution. And those still have very small probability. So it's still, though the statistic we're trying to measure is not sensitive to the distribution, the method by which we are approximating that statistic is sensitive to the distribution. So we still need to go shopping. We're not done. All right. So I'm now going to introduce to you the actual thing that this paper is sort of about, the sort of newish thing, and I'm not going to tell you how I do it. I'm sorry, I don't have time. But I am going to give you a QR code to the paper, and we're going to have a discussion period. And if you want me to whiteboard it, I can whiteboard it. All right? So here I am. I've got my initial experience, and then I've got an action, and I'm going to ask my model to give me a prediction about the next state. But it's not going to give me a distribution, because I don't care what it has to say about probabilities. It is going to give me instead maximum and minimum values for all of the features of the state. It's going to give me a bounding box over the set of possible states. And also a bounds, upper and lower bounds, over the reward. There they are. Okay? And then from there, this is the tricky part, right? Because then from there, I have to take this box of states, and somehow I have to feed it back into my model. Eventually, to get a new box and a new range over rewards. And then it gets even weirder because I have to take this box of states and feed it into my value function and get bounds on the values. So all I'm going to do right now is tell you that I promise that I can. Okay? And maybe I'll tell you this, that the simple method that the paper talks about produces conservative bounds, right? They're not necessarily tight. They're potentially loose, okay? So that's just a downside that I should acknowledge. And then we can produce similarly possibly loose bounds on the returns by just adding together these upper bounds and these lower bounds. Right? So why is it loose? Because we're sort of assuming here that the rewards can all independently reach their extreme values and all that stuff, which they maybe can't. But that's okay. I'd rather be conservative and use the model a little less than I could than be over-aggressive and suffer catastrophic planning failure. Right? Okay, so let's take a look at that. Am I over time? Is that what that means? Haha. We got there, right? So what the orange line is this, like, I'm propagating bounding boxes through my model, through my reward function, through my value function, getting bounds on the upper and lower bounds on the TD targets, and then using the range as my uncertainty measure. And the reason that it does okay in go right 10 is because it doesn't pay any attention at all to the probabilities in the model. It never once asks the model for a probability. Okay, are you excited? This is fun. Let's do it in learned models. And again, I'm not going to tell you how, but I did, I promise. So I did decision trees, and just like very quick sketch idea is like, okay, you're in a decision tree, someone gives you a box over the input, your features in the internal nodes are thresholds over those features. And so sometimes you know the answer, sometimes you don't. When you know the answer, just go down the correct branch. When you don't, go down both branches and combine the outcomes. Oh my gosh, why are you so slow? It works. It's exciting. Yeah, we're seeing, it's interesting here that like in Go Right 10, what the gray line here is sufficient. That is a learned model that has access to the previous value of the light bulb. So it could, in principle, learn a perfect model. And we see in Go Right, it is acting like a perfect model in many ways. But in Go Right 10, it just can't cope. It's too many variables, and it just has not learned quickly enough. And even that is terrible, right? And we'd rather have the worst model with better selective planning. I did it with neural nets. Maybe I won't talk to you about that. But roughly speaking, it's pretty easy to do with linear functions, and then neural nets are mostly linear functions, so it all just kind of goes through. Now, you'll notice that in Go Right 10, things got a little funky, right? So we expected the Monte Carlo methods to fall on their face, and they did not. And the paper goes into some detail about this. It turns out that what's going on there is that the neural network model is actually way worse than we ever thought it could be. And therefore, it's causing large variances where the sort of ideal model does not. And you also see the bounding box inference in Go Right 10 is doing worse than we expected, right? It kind of shrunk in a little bit. And again, the paper talks about this a little more, but I'll just tell you the upshot, which is I think there's good reason to believe that the method by which we are doing bounding box inference in neural networks is like especially overly conservative, like can give especially loose bounds. And that's what's happening here. So there's like lots more state variables, and that all the loose bounds are compounding in this case. But it's still doing okay, right? Like it's not failing in the way we feared. Let's see, where am I? How am I on time? Where's an organizer? I can.
You're like a half hour over.
For real? Oh no. Why didn't anybody? Nobody told me.
That was on purpose. I was enjoying it.
Okay. Well, I'm going to skip the Acrobat results. I'm going to just give you a. Oh my gosh. I'm sorry, everybody. I know. I have a reputation for not respecting the time limit, but that's worse than I usually am. Okay, I gave you a sneak peek. This isn't in the paper. We're still working on it, preliminary results, but like, oh, look at this. Oh, I'm so excited. It's coming. It's just very slow. I don't know why. Okay, so this is it helping in Minotaur breakout. So this is like a video game-ish example, and you can see the expectation model is failing, and the BBI, expectation plus BBI is doing pretty well. So there's a little bit of planning benefit over Q-learning, and it doesn't fail, right? Okay, exciting. So that's preliminary. Don't take that one to the bank, but I think it's pretty good. So that QR code will take you to the paper if you're interested. And okay, what did I want you to know that I held you here for an hour? Sorry. Model inadequacy matters. People don't talk about it enough, but the model is never going to be right. We have to deal with that. To detect model inadequacy, you can measure a model's outcome uncertainty. It turns out that it's important to do inference to figure out the effect of the model's uncertainty on the update uncertainty, like what you really care about. The model's predicted distribution may not mean a whole lot, right? It will want to give you probabilities, but those probabilities may not be particularly meaningful, and we probably shouldn't trust them for much. So therefore, we need distribution insensitive measures of outcome uncertainty for learned models. For instance, the range is the one that we were playing with here, but there might be others. And then finally, half an hour, oh my gosh. Finally, there is this little piece of technological, you know, like, oh, maybe you can do this. This kind of a proof of concept, bounding box inference. It does seem to kind of work in some of these pretty simple examples. All right, so there's some steps in the right direction. Okay, that's it. I'm so sorry. Thank you for your attention.